All right, let's get started. In this lecture, we will deal with Markov chains and Markov processes in general. Later, we will clarify the distinction between Markov chains and general Markov processes to get things as simple as possible. A Markov chain is a stochastic process in which the number of the states is possible states is finite, and the Markov process and the general Markov process is a stochastic process in which the number of possible states is infinite. So first of all, why do we need to deal with Markov chains and general Markov processes? We know that in a stochastic dynamic programming problem, we have exogenous shocks. We say exogenous because the shock variable walks its own path. So we want to know something about this exogenous shock process because without forming expectations regarding the future path of the shock, we don't know anything about the future actions of the agent, the behavior of which we analyze. For instance, one of the ultimate goals in dealing with stochastic dynamic programming problems is to find a policy function which is the function of the endogenous and the exogenous state. So we can calculate the expected future path of the endogenous state only if we have some expectations regarding the future path of the exogenous shock. So we need to know something about the future path of the exogenous shock, the more so because even the calculation of the policy function presupposes that we know something about the future path of the exogenous shock. So in a nutshell, we need to know something about the future path of the exogenous shock. We need to be able to form some expectations about the future path of the exogenous shock. It's a very diverse topic, and it would lead us very far. So here we only touch upon this question. The question of expectations. This is the core idea of rational expectations. The agent can form rational expectations if he or she knows the probability distribution of the shock variable. In this case, the agent and we can form undistorted expectations. Undistorted means that the expected value, the mean of the expectation, is the same as the expected value of the actual shock. So in this sense, expectations are supposed to be undistorted. However, it doesn't imply that expectations are correct. So we can make errors. The agent can make errors. This is normal in a stochastic world. What we need is the agent to be able to form rational, meaning undistorted expectations. And Markov processes is a very effective way to define a shock in a way that enables us to build a model in which the agent can form rational expectations. So this is the reason why we learn a lot about Markov chains and Markov processes. As I have mentioned, we will distinguish two forms of Markov processes. The first is a Markov chain in which the number of states is finite, and the general version of this process is the so-called Markov process, the general Markov process, in which the number of the states is infinite. Some authors use the expression Markov chain for both versions. The textbook we use make a very sharp distinction between finite Markov chains and infinite Markov processes. So we will see that a Markov process, an infinite case Markov process, is a generalization of a finite Markov chain. So this is the reason why we will start with finite Markov chains. So first of all, let's have a look at the way how we define a Markov chain. To keep things as simple as possible, we can say we need two things. We need a probability, or yes, it's a probability vector P0 that describes probabilities in the opening period, such that all the elements in the vector is strictly non-negative, and the sum of the elements in the vector is unity. And we have a transition function which is represented by an LL dimension Markov matrix or stochastic matrix pi, in which an element in the Markov matrix is the probability. So for instance, the pi ig element of the Markov matrix is the probability that starting in state I this period, the state variable goes to state j in the next period. We will have some examples very soon, so it will be clear, I promise. And each row in the Markov matrix, the sum of the elements in each row of the Markov matrix is unity. All right, and most importantly, we can use the L dimension probability vector and the LL dimension Markov matrix to calculate probability distribution for any future period. For instance, by a simple multiplication of the stochastic vector and the Markov matrix, we can calculate the probability distribution for the next period. And using this very easy way of calculation, we can calculate the probabilities for any future period. So this is a chain in this sense, because the probability distribution vector can be, for any future period, can be calculated from the probability density vector and the Markov matrix for the previous period. So it's a chain. So in this way, we can calculate probabilities for any future period. So given an initial probability density vector and the transition matrix, we can calculate probabilities for any future period. And in this sense, we can form expectations, and the agent can form expectations, because the distribution, the probability distribution, is known for any future period. It's easier to talk about a Markov chain if we have an example. So let's have an example. We have the following Markov or stochastic matrix. It's very easy to define a Markov matrix. We need two things. First, it's an LL dimension, so the number of rows must be equal to the number of columns. This is the first thing to keep in mind, and the other thing is the sum of elements in any row must be 1, must be unity. Following these simple rules, I defined a Markov matrix. This is a specific Markov matrix. And the second thing we need is an initial probability measure or probability distribution given by a vector, which is an L-dimension vector. And you can see the sum of the elements in this probability distribution vector is also 1. So by these two elements, we can define a Markov chain. And following the simple calculation method I mentioned in the previous slide, we can calculate the probability distribution for any future period. So by multiplying the probability distribution vector by the Markov matrix, we can calculate the probability distribution for period 1, period 2, period 3, and the like. We can see that in any future period, the probability distribution vector remains a probability distribution vector. So the sum of the elements in the vector is still 1, but the elements are changing. So something is going on in the probability distribution vector. We can calculate more and more expectations, and we can realize that if we calculate the probability distribution for the distant future, after a while, the probability distribution vectors became the same. So we are justified to say that these probability distribution vectors tend to a limit vector, which we can calculate by direct calculation actually. So we can find the limiting vector to which these probability distribution vectors converge. Okay, so we have a limit probability distribution vector. What happens if we start with a different initial probability distribution vector, 0.2, 0.2, 0.6? By direct calculation, we can see that we can calculate probability distributions for any future period, and we can also see that the series of the vectors, the probability distribution vectors, converge to the same limit. What does it mean? It's quite easy to interpret, and we will find the reason why it is the case. The interpretation is that no matter in what initial probability distribution we start out, future probability distributions converge to the same probability distribution vector. So we have a unique limit of the probability distribution vectors. What is the reason? To find the reason, we need to know more about the powers of the stochastic matrix pi. In the previous slide, we saw that by the powers of the stochastic matrix, we can calculate the probability distribution vector for any future period. So actually, to calculate the probability distribution for any future period, we need the initial probability distribution and the powers of pi. So let's think like a mathematician. So we have a matrix. We don't know anything about this matrix, the power matrix, and we have a vector. And we saw that by multiplying any appropriate probability distribution vector with the power of the Markov matrix, we receive the same limit. Actually, I can find only one explanation. The rows of the limit matrix must be identical. So here I show you at the bottom of the slide, I show you some powers of the Markov matrix pi, and you can see that the elements in these powers power matrices, they are changing, but they are converging towards a unique value, a unique row, and you can see that the rows in the limit matrix are identical, and yes, they are also identical to the limit vector. So what we have found is a unique invariant distribution. That means that starting in any initial probability distribution, probability distributions are converging towards this unique invariant distribution vector, irrespective of, and this is the point, irrespective of the initial probability distribution vector. So once again, what we have found is a unique invariant distribution, which is given by the rows, the identical rows of the limit matrix. To be honest, this is a very special Markov chain. It was easy to find. It looked easy to find such a Markov matrix, but this is a very special form of a Markov chain, Markov matrix, which is supported by a number of assumptions. So we need to learn more about the assumptions, what we need to keep in mind in order to define such a well-behaved Markov chain. So before moving on, we will have some further examples to identify some forms of typical behavior, some typical forms of behavior of Markov chains. A few words about the same example before moving on. There is another convergence of the powers of the stochastic matrix, which is the following average, which you can see in the slide. So if we calculate the powers of the stochastic matrix, we calculate the sum of these powers to take the average. Then the textbook says this series is also convergent by direct calculation. Use MATLAB for direct calculation. By direct calculation, it's not too difficult to find that this average is converging to the same limit matrix. So the textbook, when dealing with finite case Markov chains, make a distinction between the limit matrix of the powers of the stochastic matrix and the average of the powers of the stochastic matrix. They don't make it clear enough, I think, that the two limit matrices are the same. So sometimes, we will see it very soon, sometimes the powers of the limit matrix converge to a stochastic matrix, and sometimes only the average converges to the limit matrix. What is very important is that the two limits are the same. So in some cases, like in this case, we have two limits. The powers of the Markov matrix converges to a limit matrix, and the average is also convergent to a limit matrix, and the two limit matrices are the same. What we will see in the later discussion is that sometimes only the average is convergent, and we want to know why it is that sometimes we have two convergent series, the powers of the Markov matrix and the average of the powers of the Markov matrix are convergent at the same time, and sometimes only the average is convergent. So in the later discussion, we will clarify what assumptions we need to make the Markov chain be convergent in both senses. Let's have another example. This example comes from the textbook. So let's define the Markov matrix in this way. To analyze this Markov matrix, we need two concepts, ergodic sets and transient sets or transient states. So to be specific, we need to make a distinction. To learn what an ergodic set means and what a transient state means, let's have a look at the example on the right. Here we have two ergodic sets. The first ergodic set consists of states 1, 2, 3, and the second ergodic set consists of states 4 and 5. An ergodic set is the smallest set by definition. An ergodic set is the smallest set of states that the process has no chance to leave. So if you have a look at the probabilities in ergodic set 1, consisting of states 1, 2, 3, you can see that if the process starts in state 1 or 2 or 3, the process will never leave this set. So this is the sense in which we use the concept ergodic set. This is the smallest set that the state never leaves. The other ergodic set is ergodic set 2, consisting of states 4 and 5. You can see if the process starts in state 4 or 5, the state will remain in this set because by having a look at the probabilities in the Markov matrix on the right, you can see that starting in state 4, the process has a probability to proceed in state 4 or 5, or by contrast, by starting in state 5, the process has a chance to go into state 4 and 5 next period. The definition of ergodic set has a key term, the smallest set, because it's an option. It would be an option to regard states 1, 2, 3, 4, and 5 as an ergodic set, because when we regard states 1, 2, 3, 4, 5 as an ergodic set, we could do the same. We could say the same. The state would never leave this set. So if the process starts in any of the first 5 states, the process would remain forever in one of these 5 states. So not in one of them, in this set, in the set of the first 5 states. So we could regard the first 5 states as an ergodic set. However, we can see that this ergodic set is the combination, is the sum of 2 ergodic sets, because states 1, 2, 3 and states 4 and 5 are 2 distinct ergodic sets. So this is the reason why we regard the smallest possible set as an ergodic set, in which the process has no chance to leave. By contrast, states 6 and 7 make a transient set, because you can see that, okay, let's pick state 6 for demonstration. In this period, the state is 6. From this state, the process can go next period in state 1, state 2, and state 6. So by starting in state 6, the process can leave this state into state 1 or state 2, or it can remain in state 6. By contrast, if the process is in state 7 this period, then the process can continue in state 3, 4, 5. So it can leave state 7, or it can remain in state 7. So state 6 and state 7 form a so-called transient state, because the process has the probability of leaving this set, and this is more important, has the chance of never return, because let's have another look at the stochastic matrix on the right, and let's treat state 6 and 7 as a set. So by starting in this set, the process can continue in state 1, 2, 3, 4, 5. And let's see the columns of state 6 and 7 for states 1, 2, 3, 4, 5. It's clear that from the first 5 states we cannot go to state 6 and 7. So if the process leaves the transient, this is the reason why we call it transient state. If we leave this set, the process will never return, because from state 1, 2, 3, 4, 5 we have no probability to go back to the transient set. Okay, so we made a distinction between ergodic sets and transient states or transient sets. So on the right we have 2 distinct ergodic sets and 1 transient state, which we have a chance to leave but never return. So now we can turn back to the to example 2, to the Markov matrix of example 2. In this case, we have a unique ergodic set. State 2 and 3 form an ergodic set because if the process starts in either state 2 or 3, the process remains in those states. So we cannot go to state 1. But if the process starts in state 1, it can remain in state 1, but it can leave. You can see in the first row, gamma over 2 and gamma over 2 are the possibilities of leaving state 1. But if the process leaves state 1, it will never return. So we have an ergodic set, an ergodic state. This is state 1, and an ergodic set consisting of state 1 and state 2. So what's the point? We have a unique ergodic set consisting of state 2 and 3, and a transient state or set consisting of state 1. Just like in the previous example, we have again a unique ergodic set. In the previous example, where we didn't use the concept of ergodic sets, there we had a unique ergodic set taking up the whole state space. With direct calculation, we find that the powers of the Markov matrix is convergent to a limit matrix, the rows of which are identical. So we have found a unique invariant distribution. So for any initial measure, for any initial probability distribution vector, we receive the same invariant distribution. So this was the second typical example. Let's have the following example with a Markov matrix. Now it's easy for us to say that we have only one ergodic set that consists of the whole state space. But in this case, this unique ergodic set has cyclically moving subsets. What does it mean? Let's have a look at the Markov matrix. If we are in state 1 or 2, this period, we can go into state 3 or 4 next period. And if we are in state 3 or 4, we can only go to state 1 or 2. So this is the sense in which we use cyclicality or cyclically moving subsets. From the first 2 states, we can go only to the second 2 states, and from the second 2 states, we can go only to the first 2 states. So the state is cyclically moving between the first and the second 2 states. This is the sense in which we use the term cyclicality. With direct calculation, we get the result, which is quite shocking in light of the previous examples, that the power of the Markov matrix, the powers of the Markov matrix are different for even and odd numbers. So the series of the powers of the Markov matrix is not convergent, only the average is convergent. Likewise, the distribution vector is not convergent either, only the average is convergent. On the basis of the first 3 examples, we have some lessons, 2 lessons. First, we have as many invariant distributions as ergodic sets. So if we have one ergodic set, we have one invariant distribution. If we have two ergodic sets, we have two invariant distributions. And lesson 2, we had cyclically moving subsets in these examples. So only the average was convergent. And okay, I didn't specify it, but in this case, the invariant distribution is given by the so okay, in this case we had a single ergodic set, so we had a unique invariant distribution. But in this case, this invariant distribution was given by the rows of the limit matrix taken as the average of the powers of the Markov matrix. Later, actually very soon, we will look into the features, the qualities, the characteristics of the Markov chains that make this distinction. The next example is a quick example. We have the following Markov matrix with two ergodic sets. The first ergodic set consists of state 1 and 2, and the other consists of state 3 and 4. Just for the sake of good order, if we are in state 1 or 2 in the current period, we can go to state 1 or 2 next period. So state 1 and 2 is an ergodic set because we cannot leave these two states if we are in any of these states. And if we are in state 3 or 4, we can go into state 3 or 4. So we cannot leave the set of state 3 and 4. So state 3 and 4 form another ergodic set. So we have two ergodic sets, and the following limit exists. So we can easily calculate the limit matrix. And in this case, the limit matrix taken as the limit of the powers of the Markov matrix exists. So what we have seen previously, we can see it again. We have as many invariant distributions as ergodic sets. So in this case, we have two invariant distributions, P1 and P2. They are different. So you can see what it means that they are invariant distributions by multiplying any of them by the Markov matrix. We receive the same distribution vector. And what is more, the convex combination, any convex combination of these two invariant distributions is another invariant distribution. So that's all. This was an example in which we saw that the key thing is that we saw that we have the limit matrix taken as the limit of the powers of the Markov matrix, but we had two invariant distributions. In the next example and in the following theorems, we will clarify what to do, what assumptions we need to rule out these odd things, odd behavior in Markov matrices, Markov chains. Before turning to the theoretical parts of Markov chains, let's have a final example. This is example 5 from the textbook with the following Markov matrix. Parameters alpha, beta, and gamma fall into the open interval 0, 1, and the sum of alpha and beta is is 1. So we have the following Markov matrix. We have two ergodic sets, state 2 and state 3, and the transient set, which is state 1. State 2 and 3 are two distinct ergodic sets, because if the process is in state 2, it remains in the same state forever, because you can say in the Markov matrix that in the second row there is only one way for the process to go to state 2. So starting in state 2, the process will go to state 2, so it remains in that state. And the same is true of the third state, state 3. Starting in state 3, the Markov process, the process remains in state 3 forever. So this is the reason why we have two distinct ergodic sets. Just like previously, we could say that state 2 and 3 together form an ergodic set, but we can go further and we can say that 2 and 3 or state 2 and 3 are two distinct ergodic sets, because the key part of the definition of an ergodic set is that it is the smallest set which can be regarded as an ergodic set. State 1 forms a transient state because there is a positive probability that the process leaves state 1. You can see it in the first row. There is positive probability for the process to go from state 1 to 2 or 3, but from state 2 and 3 there is no chance for the process to go back to state 1. So this is the reason why state 1 is a transient state. The limit exists, which is quite special. So in the previous example we also had two ergodic sets, and we had two invariant distributions. It seems that in this case we have three invariant distributions. There is one invariant distribution in the second row of the limit matrix. There is another one in the third row of the limit matrix. So the limit matrix exists. It is one thing. And it seems that we have a third invariant distribution in the first row of the limit matrix, but it's not independent of the two second and third row of the limit matrix. The invariant distribution in the first row of the limit matrix is a convex combination of rows 2 and 3. So actually we have two invariant distributions, as many invariant distributions as ergodic sets. So we have two ergodic sets, we have two invariant distributions, just like in the previous example. And seemingly we have a third ergodic set, which is actually the convex combination of the invariant distributions embedded in the second and third row of the limit matrix. So before turning to the theoretical part of this lecture, let's try to summarize the main lessons of these examples. There is at least one ergodic set. Note that we are in the finite case, and in the finite case there is at least one ergodic set, and there may be one transient set at most. Later, when we move to the infinite case, we will see, and in the textbook you can also see, that we have a countably infinite case. Then it's possible to create a Markov matrix in which there is an infinite number of ergodic sets, and more surprisingly, we can create, in a countably infinite case, we can create a Markov matrix in which there is no ergodic set. So later we will make some assumptions, we will find some assumptions to rule out these extreme cases. So this is the first lesson. The second lesson, the limit of the powers of the Markov matrix may exist, but the average exists for sure. If both exist, they are the same. In some cases, both limits exist, and if this is the case, they are identical, they are equal, but sometimes only the average exists. In some cases, the process this was lesson 2, and lesson 3. In some cases, the process converges to a unique invariant probability measure, which can be calculated by the or from the initial probability measure and the power, the limit of the powers of the Markov matrix, but sometimes only the average of the vectors is convergent. So these are our main lessons. Sometimes we have some general ideas how to make sure that the limit of the powers of the Markov matrix is existent. So in some cases we can make a guess that may work, but now it's time for us to clarify those qualities of the Markov chains that lead to some forms of behavior and that lead to other forms of behavior. So this is what we will do in turn. It's time for us to underpin these findings with some theoretical work. So here we have Theorems 11.1 and 2. The first one, Theorem 11.1, is very general. So this theorem summarizes the basic features, the very basic features of any finite Markov chain. So let's have a look at this theorem to see what we have had so far. If the state space is finite, is a finite set, which means that the number of possible states is finite, and the Markov matrix pi defines the transition probabilities on the state space, we have three basic results. First, the state space can be partitioned into at least one ergodic set and a transient set. The limit taken as the average exists for sure under any condition where Q is a stochastic matrix. There is another related limit for the distribution vectors calculated with this limit taken as the average. So this is the point where we saw previously that the limit of the powers of the Markov matrix may exist, but the limit taken as the average is existent for sure. The third result, each row of Q, the limit matrix, is an invariant distribution, and the number of the invariant distributions is equal to the number of ergodic sets. And for any initial probability distribution, we have an invariant distribution which is independent of the initial probability distribution, only if the rows of the limit matrix are equal. by a convex combination of the rows of Q, we can create an invariant distribution for pi, the Markov matrix. So if we calculate any convex combination of the limit matrix, we have a stochastic matrix which we receive if we multiply it with pi. These are the basic features of a Markov chain. For instance, I like to highlight point B, under which we saw that we need to make a distinction between the limit taken as the average and the limit taken as the limit of the powers of the Markov matrix. So we need to make more assumptions if we need more results. And the next theorem, Theorem 11.2, takes us further one step ahead. If the state space and the Markov matrix are the same as previously in Theorem 11.1, Markov matrix pi has a unique ergodic set if and only if there is a state J such that for every I there exists a positive integer n with a positive probabilities in the powers of the Markov matrix. This is difficult to interpret, so a careful reading is needed. I will show you an example right away to this theorem, how this theorem works. So if the series of the powers of the Markov matrix pi is such that we can find a t, a period, for every state I, that there are strictly positive probabilities, then we will have a unique ergodic set. Let's have the example. On the basis of example 3 we have just studied, let's create another example. Let's have a Markov matrix in this form. This is a version of example 3. In this case, we have a single ergodic set, which is the whole state space S. However, we have a cyclicality in this example, because if we start in state 1, then we go to state 2, then we arrive from state 2, then we go to state 3, and from state 3 we go back to state 1. And we will walk this path over and over again. So we go over the states in 3 steps all the time. Let's calculate the first 2 powers of this Markov matrix. In this case, we have the following Markov matrix. Yes. And the third power, it is a surprise. It's very nice. Don't forget, this is the third power of the Markov matrix. And this final Markov matrix shows that by starting in any state, we will go back to the same state in 3 steps. This is what we can see in the Markov matrix, the original Markov matrix pi. So the route we walk is this. Okay, as I have just showed you. So starting in 1, we go to 2. Starting in 1, we go to 2. Starting in 2, we go to 3. And starting in 3, we go to the first state. What we can see in this example that we meet the requirements of Theorem 11.2. How, you may ask? Let me show you. Let the first, let's pick the first state. J is 1 in this example. So let's pick the first column of this Markov matrix. In this case, if J is 1, we can find for each I, for each state, an n, an integer that such that this probability, this is supposed to be n, sorry, this probability is strictly positive. So, how? If I is 1, then n is 3. n is 3. So, yes, here, this is strictly positive. We can find an integer, which is 3, for which in the first column of the powers of the Markov matrix, we have strictly positive probability. Let's go on. If I, the state, is the second, then the integer is 2. In the first column, for the second state, we can find a probability which is strictly non-zero. And last but not least, if I is 3, then n is 1. Because here you can see that in the first column of the powers of the Markov matrix, we can find a probability which is strictly positive. So in this sense, in this example, we meet the requirement of Theorem 11.2, and this is the way we need to check if a Markov process meets the requirements of Theorem 11.2. Let's calculate, we need to calculate the powers of the Markov matrix. We need to pick a state J, which means we pick a column in the series of the powers of the Markov matrix, and we need to check if there is a power belonging to each state I, for which the probability is strictly non-zero. Let's move to the next theorem, which is Theorem 11.4. The previous theorem ruled out the possibility of multiple ergodic sets, so the rows of the limit matrix, which was taken as the average, were identical. But there is a problem. We saw in example 3 that the presence of cyclicality, so if there are cyclically moving subsets behind the single ergodic set, allows only the average to converge. But as we see it right away. An additional restriction, with an additional restriction, we can exclude cyclicality. So we can make the series of the powers of the Markov matrix converge, and not only the sum will converge to a limit matrix. This is what Theorem 11.4 does. Actually, Theorem 11.4 is not too difficult. It defines an algorithm by which it's easy for us to check, to make sure if the underlying requirement is met. So if we have s and pi, as we did in Theorem 11.1, what we do is to calculate the powers of the Markov matrix for the subsequent periods, period 1, 2, 3, 4, and the like. In each power of the Markov matrix, we will go over the columns of the powers of the Markov matrix to find the lowest value in every column. These are the numbers epsilon jt for every j and t. We will sum up all these numbers for any given period. So in this case, we will have a number epsilon t which is characteristic of the given power of the Markov matrix, the initial Markov matrix. If there is a period t for which there is at least one column in the power of the Markov matrix, the lowest element of which is not zero, so if there is, in other words, if there is a period for which the number epsilon t is strictly not zero, then the condition is met. Now we can see, this is important, now we can see why it was the case in the opening example that we were converging with the series of the power of the Markov matrix to a unique limit matrix which had identical rows, because for every power, as we have seen, for every power of the Markov matrix, we had columns, the lowest element of which was strictly non-zero. They were strictly positive. So this is the reason why we had such a well-behaved Markov chain in the opening example. In the final part of this lecture, we will study Markov processes with infinite state spaces. But before doing so, before starting this phase of the lecture, it is useful for us to stop for a minute to summarize what we have done so far. In plain English, we were interested in the convergence of probability measures. We studied how probability distribution vectors converge, whether they converge or not, and in what sense they converge. So we can put a label on these accomplishments, and we can say that what we did was the study of the convergence of probability measures in general. Okay, we studied the convergence of vectors, but we can say that it was a special case of the study of the convergence of probability measures. So in general, we can study the convergence of a sequence of probability measures towards a limiting probability measure lambda. We can define two equivalent concepts of convergence of measures, of probability measures. They imply each other. One definition is given in terms of measures, and the other definition is given in terms of integrals of bounded measurable real-valued functions with respect to these measures. These definitions are equivalent, but there is a fly in the ointment. Please note that in the second version of the same definition of convergence of measures, we work with bounded measurable real-valued functions. With a counterexample, which you can find on page 336 of the textbook, we can find a case where the lack of the continuity of function f undermines the convergence in this sense, even if the series of probability measures obviously converge. So we need to modify this version of convergence, and we will say that a series of probability measures converge weakly to a limiting measure lambda only if this requirement is met for any bounded, continuous, and measurable real-valued function. So continuity of the function is added to the definition of the convergence, weak convergence of probability measures. There is another concept, strong convergence, which is studied in chapter 11 of the book, but most of the time we need to deal with weak convergence. So I wouldn't say it's not that important, it is, but we will study in this lecture, we will study strong convergence in the framework of studying the strong convergence of Markov processes. So this is what we are going to do in turn. In section 11.3, Stoke and Lucas introduce the total variation norm. This is a norm which we will use as a metric in the space of probability measures to find a way to measure convergence of probability measures. The norm is given by a supremum, where the supremum, as you can see, is over all finite partitions of S into disjoint measurable subsets. So this total variation norm is the supremum of partitioning state space S into various disjoint partitions in a way that gives the highest value to the sum of the measures over this partition of S. We are in the end game of this current presentation, of this current lecture. We are turning into the case of general Markov processes with infinite state spaces. Some notations to begin with. We have a measurable space, we have a transition function, just like previously. We have T as the Markov operator associated with P that yields measurable functions, and T asterisk as the adjoint of T that yields probability measures. Both operators were defined on page 213 of the textbook. And given these notations, we are going to study the convergence of probability measures, where convergence means convergence in the total variation norm. This total variation norm will be used to measure so we will use total variation norm as a metric to measure convergence, and convergence in the total variation norm can be given in two forms. This is what Stokes and Lucas did in section 11.3, I guess. So we have three equivalent formulations for convergence of measures in the total variation norm. Okay, I mentioned previously that the case of finite Markov chains are quite easy to treat, because in this case, so where in cases where the state space is finite, we cannot have Markov matrices with no ergodic set, or a Markov matrix where a Markov matrix that consists of an infinite number of ergodic sets. So in sum, when we move from the finite case to the infinite case, we can have some extreme examples, extreme cases. No ergodic set, an infinite number of transient states, and actually we don't need these extreme cases. So what we are interested in now is to find a condition under which we can rule out these extreme cases. This is condition D, the Dublin's condition, according to which if there is a finite measure on the state space and an integer and a positive epsilon, such that the phi measure of a set A is not higher than epsilon, then the following probability, which is given in terms of the transition function, is not higher than 1 minus epsilon. So this is the formal, very formal version of the Dublin's criterion. And as Theorem 11.9 shows, which is in line with Theorem 11.1, which was for the finite case Markov chains. So if this condition is met, then according to Theorem 11.9, we have the same basic results for general Markov processes as we did in Theorem 11.1. So we have at least one ergodic set, and the maximum number of ergodic sets is finite. The limit of the probability measures exists where the limit is interpreted as the average, and there are m invariant measures corresponding to the m ergodic sets, and any convex combination of these invariant measures is an invariant measure of the adjoint operator. So once again, under condition D, we have the same qualities of a general Markov process as we did under Theorem 11.1. Okay, let's have an exercise to show how condition D works. This is exercise 11.E, in which we have a finite mu on the state space, and we have a measurable function P on the state space given in this way, where function P is uniformly bounded away from 0, such that we have this probability, the probability of going from S to set A. This probability is given by this integral of function p with respect to the finite measure mu for any s. This is important, for any s. And set A is an element of the sigma algebra. We need to show that condition D is met. To do so, we need to highlight two things. One is that function is uniformly bounded away from 0 for any s and s prime. And the other thing to highlight is that measure mu is finite. So let's say that the mu measure of the whole state space is m, which is a positive number. By applying these results, if the mu measure of a set is not higher than epsilon, we will have the following results. So let's try to calculate. So according to condition D, what we need to show is that this inequality applies. So from the fact that the mu measure of a set A is not higher than epsilon, then the following probability cannot be higher, shouldn't be higher than 1 minus epsilon. So let's try to prove that from this inequality, this inequality follows. Let's try to show. Okay, so let's use the definition. This probability is given by the integral of function p with respect to the finite norm mu, and it's also true calculating the integral of the function over the complement. Let's pick this part of the expression and let's try to do something with this part. We are trying to show that given the fact that the function is bounded away from 0, so there is a number delta, a positive number delta, which is lower than function p. So this inequality and equality applies. From this, we can say that, picking up where we left off a minute ago, it cannot be higher than this integral. We also know that the measure mu is finite, so we need to know something about this integral. And it's true that we labeled the integral for the whole state space as m. It must be lower than m for any a which is a subset of the whole state space. Given this inequality, we can find a positive number epsilon to which this equality is true. In this case, we can write the following. we only use what we have established. So in sum, this about this probability, we know that it cannot be higher than this expression, and it must be lower than 1 minus epsilon. So not if, this probability is lower than 1 minus epsilon if this inequality is true. It's nothing new. This is what we are manipulating. So after a few lines of manipulation, we receive that epsilon must be lower than the ratio on the right. So in sum, we can say that this inequality is true of the probability if epsilon is such that it cannot be higher, it's not higher than the ratio on the right. So far, we checked that if, sorry, not phi, it was phi, no, mu. So we have checked if the mu measure of the set A is not higher than epsilon, then the following probability cannot be higher than 1 minus epsilon. The reverse must also be true. So if the mu measure of a set A is higher than epsilon, it must be the case that this probability must be higher than 1 minus epsilon. So what we need to show is the reverse inequality, and let's try to do so. So we have this probability given as the integral of function p with respect to probability measure mu. It is higher than given that function p is bounded away from 0, and this is equal to the mu measure of the integral is of the measure is equal to the mu measure of the set A. This is higher than this number, and it must be higher than 1 minus epsilon. So we need to show that it can be the case. It's an option. It's a possibility. So what we need to show that this inequality also applies, and we get to a line where epsilon must be higher than this ratio, and of course it must be lower than 1. So we have showed that the Dublin's criterion is met. This is the final slide for the lecture. We may have multiple ergodic sets, so we have some restrictions, but it may still be the case that we have multiple ergodic sets. Theorem 11.10 introduces an additional assumption by supposing that if A is any set with a positive phi measure, then for each state there exists an n, an integer, such that the probability, the n-step probability of going from S to A is strictly positive. Under this condition, the state space has only one ergodic set. And we have a final restriction provided by condition M, under which the sequence of probability measures, and not only the sequence of the averages, converge to a unique limit probability measure at a uniform rate. So this is condition M. Condition M is simple, and it must be simple to check in applications, to check if condition M is met. There must be a positive epsilon and then an integer such that for any A, set A in the sigma algebra, either that the n-step probability of going from S to A must be higher than or equal to epsilon, or the n-step probability of going from S to the complement of A must be higher than or equal to epsilon. It is easy to check, and I will show you a few examples right away to show how condition D and condition M are related. And finally, according to Theorem 11.12, under condition M, there is a unique probability measure lambda, such that iterating with the adjoint operator, we converge towards this unique probability measure. So let's have the final examples. Our final exercises come from exercise 11.5. Let's do exercise B and C in turn. According to problem B, we need to show that if we have a transition function P that satisfies condition M, that it also satisfies condition D. As you will see, everything depends on the way we define the measure phi for the conditions. We have a transition function which gives the probabilities for any n, for any s, and any n, any a, any set A. Let's find the supremum for a given A. Let's find the supremum in terms of S of these probabilities, and let it be the measure phi. In this case, it's true that for the empty set, the measure is 0, and the whole state space, the measure is 1. So once again, we have a measure which is the supremum of the transition probabilities from S to set A. We find we have a set A, and to which we find the supremum of the transition probabilities in terms of S. So we have a candidate measure. What we need to show is the implication that if this inequality holds, then it follows that the transition probability from S to A is not higher than 1 minus epsilon. So let's suppose that the phi measure of set A is not higher than epsilon. It means that the supremum in terms of S of the transition probabilities cannot be higher than epsilon, And if given that the supremum cannot be higher than epsilon, it's true that any transition probability from S to A cannot be higher than epsilon. We suppose we need to show, according to the problem, we need to show that if transition function P satisfies condition M, then it satisfies condition D. So condition M is met. So condition M, according to condition M, we know that this is true, given that it was lower, this probability was lower, it wasn't higher than epsilon, this probability must be higher than epsilon. So on this basis, we can say the following. This is 1 minus the following probability, which is lower than 1 minus epsilon, so condition D is met. Last but not least, let's have a look at problem 11.5 C. We have a state space consisting of two states, S1 and S2, and we have a transition function. This is the state space, and this is the transition function, which is simple but tricky. PSA as the transition probability is 1 if the initial state is in set A and 0 otherwise, which means the current state is not in set A. We need to show that this transition function satisfies condition D, but it doesn't satisfy condition M. So let's have a look at the transition function. As P can take on two values, 0 and 1, the case where transition probability is not higher than 1 minus epsilon means that transition probability is 0 because of, once again, because transition function can take on two values, 1 and 0. So what we need to show is if the phi measure of A is not higher than epsilon, then transition probability is 0. Okay, and if the phi measure of set A is higher than epsilon, then the transition probability is 1. Okay, so let's try to better understand the transition function. If today's state is S1 or S2, what transitions do we have? Let's try to be systematic. So this is S1 in the current state, and we can go to the same state in the next period. This has probability 1 because the current state is in the set A. Furthermore, we are in S1, and if set A consists of S1 and S2, still we have probability 1 because the current state is in set A. If we start from S1, and if set A consists of state 2, then probability is 0 because the current state is not in set A. And last but not least, if we start out from S1 and set A is the empty state, then probability is 0. Likewise, we can say the same about the transition probabilities if we start out from state 2. In two cases, we have probability 1 in cases where the initial state is in the target set, in set A. Of course, starting out from state 2 and going to S1 is impossible because the initial state is not in set A, and if the target set is the empty set, then probability is 0. Yes, 0. Let's try to find an appropriate measure phi. So, what if we say the phi measure of set A is 1 if the initial state is in set A, and the phi measure of set A is 0 if the initial state is not in set A. So actually, this measure is as simple as the transition function. It's closely related to the transition function. So let's try to figure out if condition D is met. If the phi measure of set A is 1, then the probability is 1. So if epsilon falls into the open interval 0, 1, then we can say that the phi measure of set A is higher than epsilon. If the phi measure of set A is higher than epsilon, then the transition probability from S to A is higher than 1 minus epsilon. If the phi measure of set A is lower than epsilon, then the transition probability of going from S to set A is also lower than epsilon, because the transition actually is 0. This is 0, and here the transition probability was unity. In this case, n is 1, the integer is 1, but it's okay. So we only need to have a positive integer, and we have 1. So we have a measure phi with which we can satisfy condition D. The last thing to do is to show that condition M is not met. We need to build on that aspect, on that part of condition M, according to which for every S, it must be true that this transition cannot be lower than epsilon, or it must be true of the complement, that the transition probability cannot be lower than epsilon. Let's pick state 1 as set A. Here, the possible transition possibility of going from S2 to A is 0.
And even though the transition probability to the complement is 1, so it seems to be okay, but the transition probability from S1 to AC is 0, so not for all S, condition M is met. So condition M is not satisfied because we can find a state to which condition M is not satisfied. So this is how we need to check whether condition C and condition M are met or not.